In the final segment of this section, we're going to be thinking about how we can use the integrals of some corresponding function to help us approximate the sum of a series. And in order to do that, we'll first consider a way of getting a bound on Rn, which is what we're calling the remainder term. So Rn we can think of as the tail end of the series. So if we think of the whole series as summing up a1, a2, and so on, and then those first n terms would be the nth partial sum Sn. So Rn is going to pick up for the tail end of the series after Sn. So starting with an plus 1, an plus 2, and so on, all those terms will be what we're calling the remainder, or Rn. Okay, so Rn will be the tail end of the series, starting with an plus 1, an plus 2, an plus 3, and so on. And so if we're using Sn to approximate the sum of a series, we can think of Rn as telling us how far away the series is from the actual, or how far away the partial sum is from the actual sum of the series. So that's another way to think of it, is Rn is really the error, right? It's the sum of the series minus the partial sum. And if we put them in absolute values, then we have the absolute error. So this is the error in using Sn to sum the series, or to approximate the sum of the series. And yeah, so the question is, how can we get a bound on Rn? And the way we can think about it here in this picture is we've got two ways to look at it. Notice that in the rectangles we've got the sum of the terms an plus 1, an plus 2, and so on. So in the rectangles you see that the Rn would be below the curve in this first one, where it starts at n. So in this case you can see that Rn is going to be less than or equal to the integral from n to infinity of this function. And if I just shift them over 1 unit, so then starting at n plus 1, then all those rectangles are going to be above the curve. And so now we see that the remainder term Rn is going to be greater than or equal to the integral from n plus 1 to infinity. So in this case now we have a bound on Rn. So we can see that Rn is going to be bounded between the integral from n plus 1 to infinity and the integral from n to infinity. So the actual value for Rn is somewhere in between those two integrals. Okay, so that's what this theorem is saying. It says, suppose that f of k is equal to ak, where f is a continuous, positive, decreasing function for x greater than or equal to some number n, and the sum of an is convergent. And here we're letting Rn be the sum of the series minus the first n terms of the series, so minus the nth partial sum. Then Rn is going to be in between the integral from n to infinity of f of x and the integral from the lower bound is the integral from n plus 1 to infinity, and the upper bound is the integral from n to infinity. So let's try an example where we can use this to approximate the error in using a particular sum. So approximate the sum of the series 1 over n cubed by using the sum of the first 10 terms, and then we want to estimate the error involved in this approximation. So what they're asking for is us to approximate 1 over n cubed with S10, right? So this would be 1 over 1 cubed, 1 over 2 cubed, 1 over 3 cubed, and so on, all the way out to 1 over 10 cubed. So here I'm just going to take a moment and I'll enter this into my calculator. Okay, so after evaluating this on my calculator, I get something around 1.197531986. Okay, going out to as many decimals as I get. Now let's think about the error in this approximation. So if I want to use the theorem to estimate the error, we're going to try and get an upper and lower bound on Rn. So here, let me remind ourselves up here, we know that Rn will be somewhere in between integral from n plus 1 to infinity of f of x dx on the lower end, and the integral from n to infinity on the upper end. And in this case, we're trying to approximate R10. So we'll be looking at the integral from 11 to infinity and the integral from 10 to infinity. But in this case, let's just work out the integral from n to infinity, and then we can adjust it as we need. And in this case, it's 1 over x cubed. So this will be the integral from n to infinity of x to the negative 3. So that's going to be, when we integrate, x to the negative 2 over negative 2 evaluated from n to infinity. Here I'm being a little bit lazy about my notation. Remember, this means that we're taking the limit as t approaches infinity and evaluating it at t. So this would be like, let's see, if I put x to the negative 2 in the denominator, negative 1 over 2 times infinity squared, right? This is sort of improper notation, but I'm being a little bit lazy here. And then minus negative 1 over 2 n squared. Of course, as n goes to infinity, or sorry, as t goes to infinity, this thing is going to go to 0. So the answer here would just be 1 over 2n squared. So in this case, we can see that for R10, it would be easy now to get the values, since we know on the upper and the lower bounds from 11 to infinity, from 11 to infinity for the lower bound, and then from 10 to infinity on the upper bound. Okay, so I can just put in 11 here for the lower bound. And I can put 10 in for the upper bound here. And if we evaluate these on the upper end, 1 over 2 times 10 squared, that's 1 over 200, is 0.005. On the lower end, 1 over 2 times 11 to the 11th squared would be something around 0.0041. So let's just approximate there. So that's a good approximation of the actual error, is that it's somewhere in between 0.004 and 0.005. In other words, the approximate value that we got here is off from the actual value by somewhere in between 0.005 and 0.004. Okay, so another question might be, how many terms are required to ensure that the sum is accurate to within 0.0005? Well, in this case, what we're looking for is we want Rn. We want to know what is n. We want to find n so that Rn has an error that's less than 0.0005. Okay. And what we know is that Rn here is less than or equal to the integral from n to infinity which we worked out above here was 1 over 2n squared. Okay, so we know that Rn has to be less than 1 over 2n squared. And if we want that to be less than 0.0005, what does n need to be to ensure this? So I can easily solve this inequality for n. So here, if I move it around, n squared would have to be greater than 1 over 2 times 0.0005, which would be, I think, 1,000. Right, because there I would have 3 decimal places. You had to move it. And therefore, n would have to be greater than the square root of 1,000. And roughly, what is the square root of 1,000? It's about 31.6. Okay. So we can say here that as long as n is greater than 32, so in this case we can get the desired error for n greater than or equal to 32.